Special relativity then explains a great deal. It explains why the speed of light is constant for everybody. It explains why nothing can travel faster than the speed of light. It explains nuclear power plants and nuclear bombs and lots of other things. But remember, before scientists accept a hypothesis as a theory, it needs to be tested. Well, special relativity has been tested in many, many, many ways. Let me show you just two of the ways that scientists have tested special relativity and found that it gives the correct predictions. And therefore, however bizarre it sounds to us, we need to accept it as being a reasonable explanation for the physical universe. Well, one way to test it is with the International Space Station. If special relativity is correct, the space station is orbiting the Earth at about 40,000 kilometers an hour relative to us here on the ground. So if that's true, then clocks orbiting on spacecraft should run slower than stationary clocks on the ground. And in fact, we can calculate how much they should run slower. Going to be very, 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 very small amounts, but we've developed sensitive atomic clocks that can actually measure those 100 millionths of a second. And we've put those clocks onto orbiting spacecraft. And when we do that and we bring them back down to Earth and we compare what they say to stationary clocks on Earth, it turns out that they run slower by exactly the amount predicted by Einstein. So a successful prediction, a successful affirming of the consequent. And in fact, this is something we need to take into account when we have our global positioning satellites, because those satellites up in orbit are moving very quickly relative to us, and that means that their clocks will run slower than clocks on Earth by a small amount, but by enough to mess up the very, very careful measurements that need to be made to determine exact positions on the surface of the Earth, as global positioning satellites need to do. So before those calculations can be done, special relativity needs to actually be taken into account in the equation, or in the calculations.
The Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometers above us. They move at a speed of 14,000 kilometers per hour. Each satellite follows one of 6 orbits, arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals, easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal travelled. The receiver then repeats this procedure for 3 more satellites, narrowing down its location to within a few meters.
To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created.
The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day.